Today we'll look at another way of integrating functions to obtain volumes. So this is volumes by cylindrical shells. Okay, so why need a new method? So the problem, remember, is to find the volume volume of a region revolved around an axis. So question is volume of a region revolved, obtained, say, let's say obtained volume of a solid obtained by revolving a region around an axis. Okay, so let's look at this problem now. So suppose we have a function like this, y equals f of x. So this is from 0 to some point A. We want to revolve this around y-axis. So revolve this region around y-axis. Then normally we would like to do it this way. Okay, so here we have a height here, okay, and then this thing is revolved like this, and this whole thing is revolved like this. So we find this area, and then we multiply it with the thickness here, okay, and that gives us an incremental volume. We add them up to find the volume. But here, you see, this involves finding this point. So given y here, we have to find this point and this point. So this point is x1, which is a function of y, okay? And this point is x2, which is again a function of y. So such that these are y equals f of x1 of y. Okay, so that is x1 is f inverse y. And also x2 is f inverse y. Okay, so you have to solve this equation for x. It will give you several solutions, and you will choose the appropriate ones, which one of those solutions will give you this height, the other solution will give you this height. You will also find this top point, so you will integrate this from here to here. So you'll also find this point here. So let us say this is B. So volume here, volume using this, volume will be, okay, so pi r squared here. So I'll say pi integral from y equals 0 to y equals b, x2 square minus x1 square dy. Remember, these are functions of y. Okay. And this thickness is now dy. Okay. So here the difficulty is obvious. This is the part where we will have difficulty. So instead, we want to look at the problem from a different point of view. So instead, we look at, again, the same setup. So we have this function, y equals f of x. This is 0, this is, say, a. Okay. Now what we do is, when we are turning this around, okay, so this whole line turns around here, and it gives me a cylinder. Okay, so let's do it this way. Given x here, I consider this part. So if you revolve this line, you will obtain a theoretical sphere, cylinder like this. Okay, so it will be like this. Okay, and thickness of this shell here, thickness I read as dx. Okay, so let dv be the volume of this cylindrical shell. Okay, then volume of the solid obtained by revolving this curve, black curve around y-axis, will be integral from 0 to a of dv. Okay, so it looks like we can write the volume of this in several ways. So let us attempt to write the volume of this. Okay, so if this was a real cylindrical shell, it would be like this. Okay, and here I have this. Okay, so here I have inner circle and outer circle. So inner radius, let's say R1. Let me see what I called it. Okay, inner radius R1. Outer radius is R2. Of course, I need a height h. Okay, so the volume of this shell or cylindrical shell is, I calculate the volume of the big cylinder, subtract from it the volume of the small cylinder. So the volume of the big cylinder is 2 pi r2 h. This is pi r square. Okay, so this is the final volume that we will obtain. Okay, so I calculate the base area, which is pi r2 square, multiply it by h. Okay, and then from this I subtract the volume of the other one, pi r1 square h. Okay, so this is the volume. So let us simplify this, see if we can do. Pi and h are here. I have r2 square minus r1 square. So this becomes pi h r2 plus r1 and r2 minus r1. Okay, now what we want is in this picture, you see this is the limiting position where r1 and r2 are the same. So we say that r2 is approaching to r1, or you say the thickness is, suppose the thickness is delta x. Let's give it a name. Okay, so, okay, let's call this delta x, and let's call r1 x. Then r2 is x plus delta x. Okay, so let us put this into here. Let us take this and implement it over here. So I have pi h. R1 plus R2 is 2x plus delta x. R2 minus R1x is delta x. Okay. Now when delta x is very small, okay, let me write one more thing. This is one of the ways you look at these things. 2x delta x plus pi h delta x square. Okay, so the way you convince yourself with these arguments is that when delta x is very small, much, much less than 1, then delta x squared is even smaller, it's negligible. So in the limit, here you see I'm talking about a thin shell here. Delta x squared will be considered as 0. Okay, so in the limit, this becomes, so let's say limit, this is how you invent calculus, and then you let some other people fill in the details. Okay, so this is 2 pi h x delta x, and delta x becomes dx squared. This thing becomes 0. Okay, so there are technical, logical explanation why this works. For example, we do this in exterior algebra. In exterior algebra, dx times dx is 0. Okay, because dx times dy is minus dy dx. Okay, so there are reasons why these things work, but in calculus, we convince ourselves that this will give us the result. Okay, you see that here, this thing will be very small. You integrate these things, this will not contribute anything. In the limit, you can ignore it. Okay, so this thing is actually now our dv. Okay, so here in our picture, if this is x, the height here is f of x. Okay, so this is f of x. Okay, so this height here, height of shell at x is f of x. Okay, so we found incremental volume without having to solve this equation for x. So here, finally, I have dv 2 pi x f of x dx. Okay, now, hence, volume of solid is integral of this from 0 to a in this picture, from 0 to a. And I have 2 pi, let's take 2 pi out, x f of x dx. Okay, so we compare this formula with the formula here. Okay, so here you see that these are inverses. These are f inverse y. Okay, when you solve f inverse, normally you get several solutions, and you'll have to pick the correct ones there. Okay, if your life depended on that, you do those things. But if there's an easier way for the purpose, you see that this looks more hopeful. You have an equation. Even if you cannot integrate this by hand, at least now you immediately set up the integral, and if you want a number, you can get a number. Okay, so let's see. Okay, let's solve problems now under this topic. Okay, so first problem is, so find the volume of the solid obtained by revolving the region under the curve y equals 2x squared y equals 2x squared minus x cubed, and above y equals 0. Okay, the picture will be something like this. So the picture will be something like this. Maybe it is concave up here. Okay, so we are not interested in that much. So we find this point. Okay, so here we see that at 0, this is 0. When x is small, x cubed is much smaller than x squared, so this is positive. But eventually, x cubed is dominating, so it will be negative. It goes to minus infinity. So at some point, it again crosses x-axis. So first we solve this. 2x squared minus x cubed equals 0. So here we have x squared 2 minus x equals 0. So this gives you this point, and x equals 0, x equals 2 gives the other point. So it is this point. So you want to revolve this around. Okay, so I didn't say this, around y-axis. Okay, so we revolve this around y-axis. So we use, so you see, nobody wants to solve this for x when y is equal to this. Okay, you will have 3 solutions for that. We don't want to solve this, so we'll use the other method. Okay, so at point x, let me solve this problem by demonstrating what we are doing. At a given point x, we have this height and we have this thickness. Okay, so here thickness is dx, and this is height is f of x. Okay, so you can also you can also remember these things as follows. I have here this thing, area f of x dx. Okay, this is the area of this. Then I revolve this around 2 pi x. Okay, the distance it travels is 2 pi x. This is the radius. Okay, so I have this thing here. So here you can consider it like this. Okay, so I have this thing. Okay, so this part is 2 pi x. This part height is f of x. This thickness is dx. Okay, so its volume is 2 pi x f of x dx. So that's how you can remember this. Then this is the volume I obtain by revolving this line. Okay, when you revolve a line, you don't obtain any volume, of course, but we are trying to understand the formula now. Okay, so you don't memorize these formulas, you just develop them on the spot, the easy ones, the complicated ones, okay, you look them up. So this is how we visualize the situation in our mind, and this is the volume I obtain at this point. But I have many points, so I add up all these things for all the points, and adding up continuous parameters is integration. Okay, so now that I remember the formula, I write the volume. So volume is equal to, okay, 2 pi will come out. I will integrate x f of x dx. So this is only the volume at one point, but I want to add, so from 0 to 2. So in this picture, this is 0, from 0 to 2. Okay, so now that I have this, I start putting in things. So this is x, 2x squared minus x cubed dx. The rest is easy. 0, 2. This is 2x cubed minus x to the 4 dx, which I immediately integrate, 2 pi. This is 2 over 4. Okay, let me write this 2 over 4, x4, so that we can follow what we are doing, minus 1 over 5, x5. And I evaluate that from 0 to 2 by the fundamental theorem of calculus. This is going to be the result. So let me check. I simplified this, and you get 16 pi over 5. Okay, so this is one problem. Let's look at another problem. Okay, so again, volume of revolution of region bounded by, let's see if this really bounds anything. So bounded by y equals x and y equals x squared revolved around y-axis. Okay, so in this case, again, we need to draw a picture to see which function is where. So this is y equals x. And then I have this parabola. The parabola, let me exaggerate the parabola a little bit. So this is y equals x squared. And we know that this is the point 1. They intersect at the point 1. When x is less than 1, x squared is less than 1. So that lies below the line y equals x. So this is the region. I want to revolve this around y-axis and find the volume. Okay, so in the picture, I have all the information. Integration from 0 to 1 of this thing. Okay, so volume is equal to 2 pi from 0 to 1. I have to look at the height at a typical point, x. Okay, so this is this function minus this function. So this is x minus x squared times x. Okay, let me write x here, dx. So this part is f of x times x. Okay, again, the rest is now easy. 0, 1, x squared minus x cubed dx. This is 2 pi 1 over 3 x cubed minus 1 over 4 x 4 from 0 to 1. Okay, so here you'll have 12 in the denominator, but you'll have 6, so that's 1 pi over 6. Okay. Okay, in some problems, some problems in the book come by saying that you should use the method of cylindrical shells, even though the problem can be solved in another way. Okay, so this is one of those problems. Okay, so this says use cylindrical shells to find the volume of solid obtained by rotating around the x-axis the region above x-axis below y equals something. Okay, so below y equals square root of x from 0 to 1. Okay, so in such simple calculus problems, you immediately draw a picture, x, y. So this is square root of x. It is something like this. Y equals square root of x, or the same thing as x equals y squared. I look at the region from 0 to 1. So let's say this is 1. Okay, so in that case, this point is 1, 1, if I ever need it later on. Okay, so this is the region, and we want to revolve this around around y-axis. Okay, so let's first do this by using cylindrical shells. So I have to find a shell rotating around this. Well, such a shell is going to be something like this. Okay, so this is y. Okay, so this thing is rotated around y-axis to give me a cylinder like this. Okay. So the volume of this is, I have to find this height. What is this height? Okay, what is this height in terms of y? Given y, what is this height? 1 minus equals 1 minus. What is this point? Y squared. Okay, so given a typical point here, the coordinates are x is y squared and y is y. Okay, or if you want to write it, this is x square root x. It depends on which one you are taking as a parameter. When we decide to go in this direction, we are taking the second part as a parameter. So this is my parameter, and the other equation, the other point is given by this. Okay, so height is this. And the radius of revolution, this revolution is y. And thickness, as usual, is dy. Okay, so volume is equal to 2 pi y 1 minus y squared dy. And it is from 0 to 1. Okay, because this point here, this is again 1. From 0 to 1. Okay, so this is again a simple integral. The answer turns out to be pi over 2. Let's do one more step. Pi integral 0, 1, y minus y cubed dy. So this is going to be 2 pi 1 over 2 y minus 1 over 4 y 4, 0 to 1. And according to my notes, this is pi over 2. Okay, let's use slicing. Using slices. Okay, so this time the picture is like this. I have this thing. And I consider this slice. So this slice turns around via x-axis. I calculate the area of this region, multiply it by dx, the thickness, and add up. Okay, so what is the radius of this? Okay, so here radius at x. So this point here is x. The point here is x square root of x. Okay, so height is the radius. Radius at x is square root of x. Okay, now volume, and let's say dV is area times dx. Okay, so this area is radius square, this square pi r square. Okay, so here volume is going to be pi pi integral. Again, this is from 0 to 1. 0 to 1. Radius square is, this is pi x. This is x dx. Okay, I integrate this. This is pi 1 over 2 x squared from 0 to 1, and miracle of all miracles, I get the same number. Okay, so in this problem, it turns out that this one is easier, but you don't call this difficult either. Okay, so both of them are easy. So you choose one of them. So this here we insist that you use the second method, this method, just to refresh your experience on using this method. Okay. Another problem. Okay, so these problems are are about finding the same volume with different functions. Okay, so this is for use cylindrical shells to find the volume obtained by revolving the region bounded by the given curves around y-axis. Okay, so we'll give some functions. They will bound the region. Then we'll revolve this region around y-axis to find the volume. Okay, so the first one is y equals 1 over x, y equals 0, x equals 1, x equals 2. Okay, so let's see what this region looks like. Okay, so I have this y equals 1 over 2 curve, 1 over 2x curve. Y equals 0 is this region. Okay, y equals 0 is x-axis. Okay, so this is x-axis. Now, the area between this and this curve is infinite, which we will see maybe at the end of the semester. So we should stay away both from, we should stay away from, in particular, this part. So here it says just take this part, x equals 1 and x equals 2. So this is the region that we revolve. So again, you can do this by slicing, because you see this thing is turning around. So if you take a slice here, that slice turns around and gives you a disk. The area of that disk is easy to calculate, except that you have two cases. Here, the inner radius is 1, the outer radius is 2, up to this point. This point is 1 over 2 here. And then from here to here, the inner radius is still 1, but the outer radius is 1 over x. Okay, so you calculate the areas of these disks, you add them up, you get the volume. But here we are practicing cylindrical shells. So I consider a height here. Okay, so let's say a thick height here. Okay. So this thing is revolved around y-axis to give us a cylindrical shell. So this is at x. Again, the volume is 2 pi x f of x dx from 1 to 2. And f of x is given as, so this f of x is 1 over x. Okay, so in this problem, suddenly everything collapses and we have we have an easy problem. So this is now 2 pi integral 1 to 2 dx, so this is 4 pi. Okay, so that's why you learn different methods. For example, in this problem, the previous method we learned, integrating by slices, will take a little bit longer than this one. Okay, because you have to divide the integral into two parts. None of the integrals will be difficult, but you will have to do a little bit more work. Okay, so let's do another one here. B. So here the function is y equals x squared, y equals 0. Again, it is x-axis, and x equals 1. Okay, let's see first of all if the region is bounded. X, y. So this is our usual parabola. So let me exaggerate that a little bit. Y equals 0 is x-axis, and x equals 1. So this is the x equals 1 curve, and this is the region. So in these problems, we are always revolving around y-axis. Okay, so always around y-axis. And we are using cylindrical shells. So at a typical point x, I consider this height. Okay, so height will be given by x squared. So volume, again, to remind ourselves what we are doing, we are using this formula, integral from 0 to 1 x f of x dx. Okay, so now I can put the values in. So if someone is checking or trying to understand your arguments, they know what you are doing. We are using this formula. Now instead of f of x, you'll put this thing. So this is x times x squared dx. Okay, now you integrate this. This is 2 pi. And when you integrate this, you get 1 over 4x4 from 0 to 1. Okay, so what do you get? You get pi over 2, right? Okay? Okay, so in the remaining ones, let us set up the integral. Okay, so C y equals x squared. X is between 0 and 2, and y equals 4, and x equals 0. Okay, so let us first sketch the region. So we have this parabola, and we have this is y equals x squared. We have this y equals 4. Okay, x equals 0 is this. Okay, and everything between x equals 0 and 2 is allowed. So let us look at this point. This is 2, 4. So this is 2. So this is the region that we revolve around y-axis. Now for this one, you can use slices. It will be very easy. Okay, so the height here is square root y. Okay, but then you are using pi r squared. So it will be pi x. You integrate. Then you find the surface area of the disk there, and then you integrate it from 0 to 4. That will be also easy. Okay, but using cylindrical shells, we have volume equals 2 pi. Okay, so I'm integrating a shell. Okay, so the height here. Okay, so here height at x. So this is x. So this is 4 minus x squared is 4 minus x squared. Okay, and radius is x. So this is x times 4 minus x squared dx, and x goes from 0 to 2. Okay, so this is the integral. if you check this is going to be 8 pi. Okay, let's do again here. Let's do another one here, because now I want just to set up the integrals. So here the functions are y equals 4x minus x squared, y equals x. Let's draw the figure. So it is claimed here that they enclose a region. Okay, so this is a parabola that goes, let's say, something like this. Okay, so 0 to 4. And y equals x is something like this. So this is y equals 4x minus x squared. This is y equals x. You find this intersection point. Find this point. Okay, so 4x minus x squared equals x. You easily solve this. This is 3. Okay. Now we take this region, we revolve this around y-axis. Again, we are doing the same thing. We take a line here at x, okay, and we revolve this around. So volume is 2 pi. X goes from 0 to 3. That's when this thing will make sense. X from 0 to 3. X times height. Height is 4x squared, 4x minus x squared, minus this height, which is x. So let me also put it in parentheses, dx. Okay, so this is how you set up the integral. Once you set up the integral, the rest is easy. Okay. Okay, another one. Let me check if we have time. Okay, so this one is similar to this one. This is easy. Okay, so let's now try this method on solids whose volume we already know, to check if it gives the correct answer. Okay, so for example, we know the volume of a sphere. Let us check this method. Okay, so let us check this method on the volume of a sphere. Sphere of radius r. Okay, so we have something like this. This is x squared plus y squared equals r squared. This is x, this is y, this is the region, this is 0, this is r. We revolve this around y-axis, we obtain a hemisphere. Okay, so revolving this region, around y-axis, we obtain a hemisphere. Okay, so volume of sphere is twice this volume. Okay, so volume is equal to 2 times. Okay, now I'm using this method. Okay, so this method says find this height given x. So this height is equals square root r squared minus x squared. Okay. So using cylindrical shells, the volume is 2 pi integral from 0 to big R, x times height. Height is r squared minus x squared dx. Okay. So you can now integrate this, substitute r squared minus x squared instead of u, okay, substitute set u equals r square minus x square, okay, then du is equals minus 2x dx, and we have, well, this minus 2 is not important. You can always multiply and divide by minus 2, but the important thing is, do you have x dx? Yes, we have x dx, so you can do this easily, and of course you get the correct answer. Okay, so 4 pi over 3 r cube. Okay, and the last one, let us do as the last one, the volume of a torus. Okay, so this is, well, I will not do the calculation, so maybe I can just do it here. Okay, so finally, find the volume of the torus obtained by revolving the given disk around y-axis using cylindrical shells. Okay, so what we have is something like this. At a distance, I think I'll use big R here. At a distance big R from the origin, from x, y, I have a circle of radius small r. Okay, I revolve this around y-axis, so I obtain a torus like this. Okay, so this is the standard way to denote a torus. Okay, so the volume, I take height. Okay, so let's take this height. So equation of this, what is the equation of this? This is center. Equation of this is x minus r square plus y square is equal to small r square. Okay, so that's the equation. Then this height, you have to solve for this height. Okay, so from here, I have y, height is y, so y is equal to, okay, so r square minus x minus r square, okay. And actually the total height is twice that, okay, so this point is the positive one, this part is the negative y, so height is, so this height is 2 times this, r square minus x minus r square. Now, I calculate this height from this point to this point, so I need to find this point also. This is r minus r, and this point is r plus r. Okay, so these are the end points. Okay, so all the problem is now solved on the figure. So volume by cylindrical shell is 2 pi integral from this point to this point, r minus r, r plus r. I multiply x times height. Height is this, 2 r square minus x minus r square dx. Okay, now the rest is again do some substitution. You can substitute. I think you'll do substitution twice. Okay, so first thing to think about is x minus r. Okay, you substitute this, you get an integral. In that integral, you make another substitution because here you'll have u square. Okay, so if you want, you can do the substitution from the beginning. You can call this whole thing u square. This whole thing x minus r square u. So well, that will be a little bit more complicated. So do it step by step, and you will get at the end 2 pi r times pi r square. Okay. You look at this and you discover a theorem. you see this is the distance, the center of mass of the figure traveled, and this is the area of the figure. Okay, so this is a 2,000-year-old problem, theorem, Pappus theorem. If you revolve a figure on along a distance, the distance is center of mass travels, then the volume obtained is that distance times the area of the region. Okay, so this demonstrates this is verification of Pappus theorem. Okay. So if you knew Pappus theorem, you could calculate this without using an integral. Okay, but the bottleneck in Pappus theorem is to find the center of mass of the figure. If this one is totally trivial, you have a circle, the center of mass is the center of the circle, and it obviously travels 2 pi r, so distance times area. Okay, so let's take a break here and nothing new.